All right, so today we move on to lesson 5, which is called Ohm's Law. So hopefully you finished the lab already because we're going to use that today. So, quick review. When we talk about voltage, what do we actually mean? Well, voltage is defined as the electrical stored energy per unit of charge. So it's the amount of energy present divided by the number of charges. We measure it in volts. So 1 volt is a joule per coulomb. And like gravitational potential energy, voltage always is relative to a point. And so in a circuit, we usually call that point ground. Just like when we're talking about potential energy of something, we'd say a ball has 10 joules of potential energy relative to the ground. So it's relative. Sometimes voltage is called the EMF, or the electromotive force. So if you're looking at other online references, sometimes it's called that because remember, it's basically the push. And so that's kind of the most important thing to gain from all of this. When you think about voltage, think voltage is really the push that makes charges flow. And the higher the voltage, the more push there is on the charges that makes them want to flow. So that's a quick review of voltage. Current is defined as the amount of charge that flows past a point in a given unit of time. We measured in amps, and an amp was a coulomb per second, so 1 coulomb of charge flowing by a point in 1 second is a current of 1 amp. And the direction of current is the direction positive charges would flow, that is, if they actually moved, which they don't. So we also talk about electron current sometimes, but conventional current is the direction of positive charges would flow. So the question we asked in lab was, how does the flow of the current depend on the voltage? In other words, if we increase the push on the charges, the voltage, what happens to the flow? So we did this in lab with a little simulator. Sorry you couldn't do it by yourselves in class. It's a whole lot more fun to swap out batteries and measure the current and see the light bulb and glow and stuff, but we're doing the best we can here. So here's kind of what we got. If you graph current on the y-axis because it was the dependent variable and voltage on the x-axis because it was the independent variable, I think you found in lab that there was a direct relationship. And you can model that by an equation which looks like this. It's proportional. The current is proportional to the voltage, and this k right here is the slope of the graph. Now, if I were to calculate k for a particular lab, I might get something like this. So some of you got 0.025 as your slope. So just think about the units for a minute. When you're finding slope, you're finding rise over run. So the rise is measured in amps, and the run is measured in volts. So the slope is amps per volt. So we're saying the slope is 0.025 amps per volt. That's going to be important. All right, so this leads us to Ohm's law. So Johannes Ohm was a Dutch physicist who had a number of interesting discoveries. He discovered the proportional relationship between current and voltage. And he's also the guy that was able to supercool helium enough to discover superconductivity. So that was kind of cool. What we found was that the current is proportional to the voltage. And we want to know, what do we do with the slope? Well, the slope turns out to be the conductivity. If you have a small slope, you have a small conductivity, and a large slope means there's a large conductivity. So we call the slope the conductance of the circuit, and the units are amps per volt. But we don't always work with conductance. The more familiar term is resistance. So let's talk about how we get there. Generally, we like to think about how much voltage you would need to get a certain current to flow. So if you knew your current that you needed in a circuit, and you knew the conductance, how much voltage would you need? Well, if you solve this for voltage V, you got to multiply both sides by 1 over k, or divide both sides by k, you would get this. The voltage equals 1 over k times the current. All right? And so we call this 1 over k, we call that the resistance. So if k is big, if the conductivity is big, the resistance is small. So if we call the resistance 1 over k, we can rewrite this equation as V equals R times I. So V equals R times I. And then typically we switch the order of the R and the I. That's allowed because of the commutative property of multiplication. And we can write that using Ohm's law. So let's talk about resistance for a minute. Resistance is a measure of how difficult it is to accomplish a task. So if there's a lot of resistance, that means it's hard to get it done. And if there's no resistance, it's easy to get it done, right? For charges, resistance is a measure of how difficult it is to make the current flow. So if you have a high resistance, it means it's very hard to get electrons to flow, like rubber or wood. If you have a low resistance, then it's easy for the electrons to move. So that's like a metal, or maybe some salty water. And if you had zero resistance, it would mean it's not hard at all. It doesn't take any effort to make the electrons move, and that's actually superconductivity. So when we talk about electrical resistance, we're talking about a measure of how hard it is for current to flow. So resistance has a unit of volts per amp. So a volt per amp is going to be defined as an ohm in honor of Johannes Ohm. And we're going to use this goofy looking symbol, looks like a horseshoe, for ohms. It's actually called omega. It's the Greek letter. It's basically, you can kind of just make a horseshoe. And that's the symbol for resistance. That's the unit of resistance. We call it ohms, and it's really just volts per amp. Okay? So a resistance of 100 ohms means it would take 100 volts to get a current of 1 amp to flow. If the resistance was 500 ohms, that's more resistance. That means it would take 500 volts to get an amp of current to flow. So the resistance measures the difficulty of getting the current to flow in the circuit. So you need a higher voltage to make the same current flow if the resistance is higher. So here's what we get. V equals I times R. So I is the current, R is the resistance, and this is actually the big idea for the unit. If you had to say, what is the most important equation, what's the biggest big idea in this whole unit, it's this. It's called Ohm's law. And it says that the voltage is proportional to the current, and the proportionality constant is the resistance. V equals I times R. So the voltage is going to be measured in volts, current is going to be measured in amps, and resistance is measured in ohms. And we don't usually write ohms, we usually use the omega symbol. So here's kind of what's going on. This is a great little analogy of what's going on in a circuit. It's a gravitational analogy, but you can think of the battery as like an escalator. It takes charges and it adds energy to them. So when the charges get here to the top of the escalator, they have energy. They flow along the wire and they don't lose any energy while they're flowing along the wire because they're not going downhill. But when they get over here to the load, this is the thing that needs their energy that's going to do work for us. This could be a flashlight, this could be a radio, this could be a motor. Who knows what it is that needs the energy, but we call it the load, and it has a certain resistance. It offers resistance to the flow. And so as the electrons go down the hill, they do work for us, and when they get to the bottom of the hill, they're now out of energy. So they roll along till they get back to the battery or the power supply, and that adds energy to them. So this is a model of a complete circuit. The battery adds energy, and that energy is transported by the wires to the load, which uses up the energy to do something for us that's useful. Okay? So that's what we call the model of a circuit. Now, we're going to represent that schematically. Here is the escalator, the pump, the battery that adds energy. The wires carry the current without losing any energy. And then we draw this little zigzaggy pattern as the load or the resistor. It's the thing that's getting the energy, that's using up the energy. And then the circuit has got to be complete in order for the charges to get back to be lifted back up to a higher energy level, and then they go back around. Okay, so this is going to be our schematic showing a simple circuit that has a voltage source, the current is the flow, and the resistor is the load, and we usually draw squiggly lines like that to represent it. Now, quick review, we're going to use this equation too. The power, which is the rate that energy is transferred, is also equal to I times V. That was lesson 4. We already practiced some problems with that, but we're going to use it, so I stuck it in there to remind us. Okay, resistance comes from materials, and it has to do with their electrical and their chemical properties, and this is a fun lab to do, but we don't have time to do that. E-learning is really slowing us down, so we're actually going to skip this part and just motor on. Let me solve 2 example problems for you. The first one is an automotive headlamp, so this is like on your car. It has a resistance of 3.5 ohms. And I want to know how much current will flow in the bulb when it's connected to a 12-volt source. So your car battery is 12 volts. So the first thing we do is we draw a little schematic. Here's the escalator, the thing that's adding energy to the charges. The charges go around the circuit and they lose energy in the headlamp, and then they go back to the battery and get energized and then go round again. Okay? There are 4 variables we're going to use. We have the voltage, the current, the resistance, and the power. And a reading of the problem will help you quickly determine that the voltage is 12 volts and the resistance is 3.5 ohms. And so the first thing we want to do is find the current. So that's pretty easy. We know the voltage and we know the resistance. We're just going to solve this for the current I. So we can manipulate our equation. I is V over R. Plug in our numbers, stick that in our calculator, and we get 3.4 amps. So the current flowing in this light bulb is 3.4 amps. The second thing we want to know is at what rate will the energy be converted? So the thing you got to know is when somebody says at what rate will energy be transferred or at what rate will energy be converted, you got to know that's power. Okay, power is the rate energy is transformed. So you got to know that. So what we're really asking here is for the power. So that's pretty easy. The power we know is I times V, and since we have I and we have V, that's easy to evaluate. We plug in the 3.4 amps for the current, 12.0 volts for the voltage, and that gives us 41 watts. So the automotive headlamp is rated about 40 watts, 41 watts. All right? All right, next problem. We have an incandescent light bulb. So this is the old-fashioned light bulb where the electricity just went through a little tiny loop of wire, which was actually loops of wire, and these got really, really hot when the electricity passed through them, and they glowed, and that's what made the light. They're terribly inefficient. 75 watts, you might be getting 5 watts of light and 70 watts of heat. So really, these old-fashioned light bulbs, incandescent bulbs, were really just heaters that gave a small amount of light on the side. Nowadays, we have much more efficient lights, LED lights, which give you mostly light for your energy. But anyway, we connect it to a 120-volt source, so that's like your household wall plug, and we want to know what is the current and the resistance of the light bulb. Okay, so we draw a little schematic. Here's the source of our energy. It's going to flow through the circuit. It's going to lose energy here as it gets turned into light and heat, and then flow back to the wall. A quick reading of the problem helps us fill in the variable list. We know that the power is 75 watts because it says the energy is dissipated at a rate of 75 watts. That's the power. We know the voltage is 125 volts. We don't know I and we don't know R. And so now here it gets a little tricky. Like, what do you solve for next? So here's the 2 equations we have. So let's look at the first one. Do we know the voltage? We do. We know the voltage, but we don't know the current and we don't know the resistance. So this equation is not going to help us yet. So let's go here. Do we know the power? Yep, we know the power. And we know the voltage. So we could solve this equation for I. Once we had I from this equation, we could then use this equation to solve R. So sometimes when you're solving problems, you just got to kind of write down the equations you have, and it's a little bit of a puzzle. You got to kind of figure out what it is you have and where you need to go and get to. So here's what we have so far. And so the first thing we're going to do is we are going to solve P equals I times V to find the current. So we know the power, we know the voltage, we can find the current, it's P over V. We plug in our numbers, 75 divided by 120 is something less than 1. Work it out and you get 0.625 amps. So the current in this incandescent bulb is 0.625 amperes. Now the second thing we want to do is try to find the resistance. So V equals IR. And now we know the voltage already, and we just found the current, so finding the resistance won't be terribly hard. The resistance is going to be the voltage divided by the current. Plug in our numbers, 125 over 0.625, and you get 192 ohms. So the resistance of this light bulb, this tiny coil of wires, which we call the filament, the resistance turns out to be 192 ohms, or 192 volts per amp. Okay? So there you go. That's how we solve problems using Ohm's law, and that's how we evaluate and analyze basic circuits. So the next assignment that's waiting for you is some practice solving problems using Ohm's law. That's V equals IR. and also using the power equation, P equals IV. So your variable list is going to look like this for every single problem. And as you read the problem, figure out what you know and then figure out how you can find what you don't know. All right? Okay, good luck.